El doctor es especialista de un área, estudia el área subatómica, lo pequeño, muchas veces no visible a lo humano, ¿verdad? La división. Me gustaría que él sea como una guía nuestra y que nos explique de manera literaria, de manera poética, cómo ve el mundo subatómico, cómo se ve el mundo subatómico.
To be honest, we are not only working subatomic, but also on the atomic level, and so with molecular systems, which you can also visualize nowadays, right? In the old days, the atomic theory was developed before people were able to see atoms, but nowadays it's possible to see atoms in a molecule with modern devices. So one could imagine that at some future way we will also be able to see even more than we can see nowadays. And the particles which are measured, for instance, in high energy physics, one sees nice tracks of those subatomic particles, right? So we don't see directly the particle, but the tracks which they are forming, and then we can conclude what the particles are. And what we try to do in the research which we are doing is not that we use very high energies and then see what we can produce there, because for this you need huge colliders like the CERN and other places. But we like to do spectroscopy on something which is stable and try to learn how the subatomic particles are interacting with each other, what their signatures are, and maybe if we can see something from cosmic field on the level of molecular systems. So that is what we try to do in our research.
Haga cuenta que soy ciego y que él me lo diga de manera literaria o como escoja él, que me diga, este es el mundo que te estás perdiendo.
So maybe as an example from history, which is not precisely our own way of doing research, is sometimes you know that there must be something, although you don't see it directly. So for instance, historically, people have formulated a particle which was called the neutrino, because they assumed that there is a certain conservation of momentum, linear momentum, and then they saw that if I measure all the particles in coincidence which I know, that they simply don't add up, right? So you see, if you stretch something apart, you measure this momentum, you measure that momentum, but you see, oh, all of a sudden they are not going in this direction, but they go like this. Then they say, okay, there must be a third particle. We have not seen it, and let's call it the neutrino. And then people start to think, how could I detect this if this is a particle? And then they are building devices and try to measure this, right? And this is a type of, you have sometimes indirect evidence there must be something, although you have not seen it directly. And this is the driving force of our research. So we question everything, so to speak, and say, what if, right? There were some things which we currently assume they should definitely be preserved, like momentum, linear momentum conservation. But how could we test if maybe there is something wrong with this assumption, right? And which kind of experiments could we do? Normally we are guided by some ideas, right? So like when people were searching for the Higgs boson, which has not been seen before, they had an idea at which mass to look, at which energy and so forth, right? And we are also typically guided by ideas.
Hypothesis.
Yes, and then try to check. But sometimes it is not clear how large the effect should be. And this is where we come into play, because we try to calculate which molecule, for instance, would be possible to make the effect very large so that we can see it even if it's very small in the beginning, right?
Por lo que pudimos saber, el estudio que usted realiza consiste en utilizar moléculas hechas a medida que generan campos internos que son importantes para el estudio de la materia. ¿Cómo se crea una molécula a medida?
For our specific research, we just create them in the computer and calculate the properties. But of course we calculate only things which also our colleagues will be able to synthesize in the lab. And now it can be very different routes to do the synthesis, either really traditional chemical synthesis, where people fill in a flask certain substances, let it react, stir it for a while, heat it up, and then you extract the compound which you would like to have. Or some techniques which are only taking place in the gas phase, where we let collide individual atoms and then they form the molecule which we would like to have. And that depends really on the purpose which we would like to have, or which we have for our systems. And this makes also the research so exciting, because we can work together with experimental chemists who produce those substances, which are sometimes more complicated, and we can work with physicists who have a completely different approach and use colliders in order to produce a certain radioactive element which lives only for microseconds, and then we continue to work with this in an apparatus, and the whole experiment is over in maybe milliseconds or so.
Esos campos internos que se generan con estas moléculas hechas a medida, serán distintos como moléculas haya seguramente, ¿no es cierto? ¿Cuántos de esos campos se han podido estudiar y qué tipo de fuerzas prevalecen en esos campos?
The fields which we have typically, which we worry, are electromagnetic fields which are created, and each atom is, so to speak, giving rise to an electromagnetic field in which all the particles are moving, right? So because they have a charge and so forth. And we try to make, for instance, a huge electric field possible in which an unpaired electron is moving, for instance. This is what we try to predict. And to see that this internal field, which the electron fields, is as large as possible, and that we then can see signatures of certain interactions which we haven't seen before. That is one direction. The other is to use molecules which are not mirror images of each other, like the left hand and the right hand, so that they are not the same when you mirror them, but non-identical. And they can see something which, so to speak, is a signature of not only the electromagnetic interaction, but also the weak interaction, which is one of the four forces which we have, right? Electromagnetism, weak force, then there's a strong force and gravitation, and we have worked on the electromagnetic and the weak force so far, but we are also looking at what comes from further unification with the strong force, or cosmic fields, which can be dark matter, for instance, and that we try to detect with molecules.
¿Cuál es la última teoría formulada por usted y por el equipo con el que trabaja?
We are not so much formulating a new theory, we are testing possible theories which go beyond what we know at the moment. So that is, our job is not to devise a new model, but rather what kind of ingredients should be put into a new model. So for instance, certain theories say that there is an electric dipole moment of an electron, which is larger than what our current theories say. And now there are many different theories available which predict all larger effects, but we just say, if this effect is there, how would it be magnified in a molecule, right? And then people try to measure. From this we can see which kind of electric dipole moment an electron would have. And then we can say, oh, this theory is ruled out because it predicts a way too small one, or it predicts something which is much too large, we should already have seen it, and so forth. So we are not developing theories ourselves. We use our theory in electronic structure in order to predict what would we see from a new theory. We use a technique which is based on two components, as we say. This is very technical, unfortunately, but which is, so to speak, a certain variant which we use, which is, in our opinion, very efficient, so that we can quickly calculate different properties in many different molecules, and we can very fast say, this is a good candidate, this is maybe not a good candidate, and we can include very fast also new properties. When someone says, oh, there could be something like this, then we can immediately put it into our theories and try to calculate.
En química orgánica podemos decir que una molécula es quiral cuando ella y su imagen en un espejo no son superponibles. Usted trabaja en el tema de la quiralidad molecular y acá viene la pregunta. ¿Esto se debe a que las fuerzas nucleares débiles son las que dominan el mundo atómico y ellas no presentan quiralidad? ¿Podría desarrollar esa idea?
So that's a different. So the chirality is just defined as this property. So if you can take an object and not superimpose it on the other, you call it chiral. It does not explain where the chirality comes from, right? So why does this have the chirality? And there are two different ways to explain it. There is one possibility that you spontaneously fall to one of the two sides. So you start with something which is achiral, and then all of a sudden this happens and only this one remains, right? So it's spontaneous either there or either there. That's one possibility for forming chirality. But some hypotheses that there is a difference between left and right. One of them is more stable energetically than the other. And then it would be natural that we have this or that because they are no longer the same energetically, but rather that's one, that's the other. At the moment there is no best. Because as a scientist, each hypothesis is a hypothesis until you rule it out, right? Then the hypothesis is gone. And there are some people who have preferences and who say, oh, this is the explanation, that's the explanation. I not.
Un efecto que predice el modelo estándar de la física es el de la violación de paridad. Si bien en esa predicción es teórica, no se la ha encontrado experimentalmente aún. Uno de sus temas de investigación es el de la violación de paridad. ¿Qué tan cerca estuvo de comprobarlo experimentalmente?
A parity violation has been observed, but not this for the chiral molecules. In molecules, it has not been seen. So on the atomic level and also on the particle level, parity violation was observed, but for molecules, it was not yet observed. And we are now predicting molecular systems which can be hopefully measured, where one can see the effect for the first time. And the first experimental attempt was already made in 1975. So quite a long time ago, right? 50 years ago almost. And since then people try to measure the effect, but it was not yet possible. So I'm not an experimentalist, we are only predicting. We propose experimentalists which molecules to do, and we are collaborating with experimentalists who really do a measurement on this, right? And so who have precision spectroscopy, and we have a network in which we are working precisely on this kind of measurement. And so we have good candidates meanwhile, and we are trying to work on this. Oh, we have already a couple of candidates. So we know molecules which are candidates which are reasonably good, and we are still trying to improve further, but we have a couple of candidates which are very good. One is achiral. It's radium fluoride. It's a diatomic molecule where we have done also with experimental colleagues now measurements, and others are chiral. The other is, at the moment, we have just published a paper on a rhenium complex where people did the spectroscopy. That means one has to improve further in order to see something. And we have proposed some very heavy elements, or very heavy elemental molecules, which can also be reasonable candidates.
Hace poco apareció un nuevo integrante del mundo subatómico, que es el tema de los muones. En Chicago hace poco se publicó, bueno, en Chicago fue la experiencia y se publicó en una revista de física la aparición de unos muones muy inestable, de vida efímera. ¿Cómo interviene este nuevo actor en los estudios que realizan? Que a partir de los muones parece que estarían dadas las condiciones para formular una quinta fuerza fundamental de la naturaleza.
There are a couple of experiments which try to do so, and we are also discussing about our molecular systems to look for signatures of a fifth force. If I'm not entirely wrong, it's not yet conclusive, right? So there are just tests which one is doing, and the muon has a nice feature that, for instance, if you have muonic molecules, that the muon is very close to the nucleus, so you probe more of the properties of the nucleus. And I remember that there was an experiment also with terbium fluoride where people were looking at different isotopes and were trying to see signatures of the fifth force from this. My personal perspective on this type of research is that it's very complicated in the way it is currently doing, because you don't see an additional violation of a symmetry, which is normally very clear signature. So if you see parity violation, you have a broken parity, right? If you see CP violation or PT violation due to some new interaction, then it's a clear signature. With the fifth force, most experiments I know of, which does not mean that it's that I have all the knowledge there, that means then you try to see deviations from the normal behavior by, say, modification of the width of some interaction. And so then you have to have understood everything on an extremely perfect level in order to be able to tell here is the signature of the fifth force. And for the, if I'm not entirely wrong, this experiment which was published 1 or 2 years ago, I think people were looking at ytterbium, at calcium atoms, and then later on people said, yeah, but it can be normally explained without a fifth force by that and that mechanism. So it's very difficult to find a conclusive signature. To illustrate, it is when you do an experiment and you have the left and the right hand, to say there is a difference, that is very easy. But to say, oh, both have been lifted by the same amount a little bit, that's very difficult, because you have to know very precisely what is ongoing. Whereas if you see a splitting, you see immediately, oh, there's something going on. And this is a problem with all those effects which are just additive to some other effect, that it's very complicated to rule out that it's not a normal mechanism and can be simply explained by what we already know.